VT Basic Unit STS1, Electrical, /OC1, Optical, STM1 Base Bitrate MBPs Payload Container Virtual Tributary, VT, Virtual Container, VC, Frame Dimensions 9 rows x 90 columns 9 rows x 270 columns T1 Support Native, via VT 1.5, Supported, via VC 11, E1 Support Complex Mapping Native, via VC 12. Framing and terminology. Both systems use a 125 microsecond frame, but they name their parts differently. Overhead. In SONET, the overhead is split into section, line, and path. In SDH, it is split into regenerator section, multiplex section, and path. The container system, asterisk in SONET, the small envelopes used to carry T1s are called virtual tributaries, VT 1.5. In SDH, the envelopes used to carry E1s are called virtual containers, VC 12. Hierarchy and scaling. Scaling in both technologies involves multiplexing the base frames by multiples of 4, with a few exceptions. SONET level SDH level bitrate STS3/OC3 STM1 MBPs STS12/OC12 STM4 MBPs STS48/OC48 STM16 GBPS STS192/OC192 STM64 GBPS. Note, OC stands for optical carrier. In SONET, OC3 refers to the light signal traveling on the fiber, while STS3 refers to the electrical signal inside the equipment. In SDH, STM is used for both. Why they are compatible today despite the different names, the frames were engineered to be interworkable. Since an STM1 frame is exactly 3 times the size of an STS1 frame, a transatlantic fiber link can carry SONET traffic from New York and hand it off as SDH traffic in London. The equipment simply maps 3 STS1s into one VC4 payload inside an STM1. The transition from PDH, plesiosynchronous digital hierarchy, to SDH, synchronous digital hierarchy, was the most significant leap in transport history. While PDH was sufficient for simple voice links, it became a bottleneck as networks grew. SDH replaced PDH for 4 fundamental reasons: synchronization, efficiency, management, and reliability. The multiplexing mountain, efficiency. In PDH, the clocks are only nearly in sync, plesiosynchronous. To extract a single 2 Mbps, E1, signal from a 140 Mbps, E4, stream, you had to demultiplex the entire stack, E4 4x E3 E3 4x E2 E2 4x E1. This required a massive mountain of hardware, back-to-back multiplexers, which was expensive, consumed high power, and introduced latency. The SDH solution, because every node is perfectly synchronized to a master clock, SDH uses pointers. This allows the hardware to see exactly where an E1 is located inside a 155 Mbps, STM1, or even a 10 Gbps, STM64, pipe and pull it out directly. This is called add-drop multiplexing, ADM. Standardization, global interoperability. PDH was a mess of regional standards. A T1 from the USA could not easily connect to an E1 from Europe because their hierarchies were completely different. PDH, North America used T carriers, Europe used E carriers, Japan had its own variation. SDH, it provided a unified global standard. An STM1 frame is the same in London as it is in Tokyo, allowing international fiber optic cables to connect seamlessly across borders. Operations, administration, and maintenance, OAM, PDH was a dumb pipe. It had very little overhead, meaning it couldn't tell you much about its own health. If a line failed, engineers often had to physically go to the site with testers to find the break. The SDH solution, SDH reserves about 5% of its bandwidth specifically for overhead. Performance monitoring, it constantly checks for bit errors. Remote management, an operator in a central office can configure a circuit thousands of miles away without touching the hardware. Order wire, it includes dedicated voice channels for technicians to talk to each other between stations. Self-healing reliability. PDH networks were typically point-to-point. If the fiber was cut, the service stayed down until it was manually repaired. The SDH solution, SDH introduced the self-healing ring. Using protection protocols like MS Spring or SNCP, the network can detect a fiber cut and reroute traffic in the opposite direction around the ring in under 50 milliseconds. This automatic switching made the internet and phone systems resilient enough for critical infrastructure. Summary table, PDH versus SDH. Feature: PDH, the old way, SDH, the modern way. Clocks: independent, plesiosynchronous, master-slave, synchronous. Extraction must unpack everything direct add-drop via pointers. Standards: multiple, T1, E1, etc. 1 global, STM, monitoring very limited comprehensive, overhead, recovery manual intervention automatic, 50 milliseconds. In 2026, the status of SDH, synchronous digital hierarchy, can be described as the long sunset. While it is no longer the technology of choice for new network builds, it remains a critical legacy layer that refuses to disappear entirely due to its unmatched reliability in specific sectors. The decline, from core to edge for nearly 2 decades, SDH was the king of the telecom core. Today, its role has shifted. Replacement in the core, massive WDM, wavelength division multiplexing, and OTN, optical transport network, have replaced SDH in the backbone. Where an SDH line maxed out at 10 Gbps, STM64, modern OTN links handle 400G to 1.2 T per wavelength. The rise of all IP, with 5G and cloud services, traffic is now natively packet, Ethernet/IP. Carrying these bursts of data inside the rigid, fixed-size containers of SDH is incredibly inefficient, the IP over SDH tax. Where SDH still lives, the hard pipe strongholds, there are 3 main islands where SDH equipment is still actively maintained and even purchased: A. Critical infrastructure, power and rail. Power grids and railway signaling require deterministic latency. They need to know that a trip signal to a circuit breaker will take exactly 2 milliseconds every single time. Because SDH uses physical time slots rather than packet buffers, it provides a hard pipe that Ethernet struggles to match without complex tuning. B. Government and military. Many secure communication lines and red/black encrypted networks were built on SDH architectures. These organizations often stick to SDH because it is air-gapped by nature. You cannot hack a TDM time slot the same way you can attack an IP header. C. Legacy enterprise services. Banks and large corporations still have old PBX, office phone, systems or mainframe links that require E1 or T3 interfaces. As long as these customers pay for these high-margin leased lines, carriers will keep the SDH hardware running. The modern solution, FGOTN, fine-grain OTN. The biggest news in 2025 to 2026 is the standardization of FGOTN, fine-grain OTN. This is widely considered the successor to SDH. The problem: traditional OTN was designed for big pipes, 100G. It couldn't efficiently carry a small 2 Mbps E1 line. The solution, FGOTN, allows the network to carve out tiny, fixed bandwidth hard pipes, down to 10 Mbps, inside a 100G or 400G wavelength. The goal: it allows carriers to finally turn off their old, power-hungry SDH shelves and move those legacy E1/T3 services onto a modern, power-efficient optical platform. Current challenges: the spare parts problem. The primary status of SDH for most operators is maintenance mode. End of life. EOL. Most major vendors, Huawei, Nokia, Ciena, have moved their SDH products to end of support. Skills gap: the engineers who grew up configuring SDH are retiring. Younger engineers are trained in Python and IP, not in manual TDM cross-connects. Power consumption: old SDH hardware is physically large and consumes a lot of electricity compared to modern high-density pizza box routers. Summary of SDH status aspect. Current status, 2026, new deployments near zero, except for power/utility niche, traffic volume dropping rapidly, shifted to IP/Ethernet, replacement tech OTN, FGOTN, and segment routing, SRv6, equipment state aging, being replaced by packet optical platforms. Framing of STM1. The STM1, Synchronous Transport Module Level 1, frame is the basic building block of the SDH hierarchy. It is a digital structure that repeats 8,000 times per second. To visualize it, engineers represent the frame as a 2D grid of bytes. The STM1 grid structure. The frame consists of 2,430 bytes, arranged in 9 rows and 270 columns. Total bitrate. Orientation: the bits are transmitted row by row, from top to bottom and left to right. The section overhead: so, the first 9 columns of the frame are reserved for management. This is split into 2 distinct parts by the pointer row. RSOH, regenerator section overhead, location, rows 1 to 3, columns 1 to 9. Function: this overhead is handled by regenerators, devices that just boost the signal. Key bytes, includes the A1 and A2 bytes, framing patterns used to find the start of the frame, and the J0 byte, section trace to ensure the fiber is connected to the right neighbor. MSOH, multiplex section overhead, location, rows 5 to 9, columns 1 to 9. Function: this is handled by multiplexers, the brains of the network. It is ignored by simple regenerators. Key bytes, includes the K1 and K2 bytes, automatic protection switching to trigger the 50 millisecond self-healing, and B2 bytes, for error parity checking. O pointers, administrative unit pointers, location, row 4, columns 1 to 9. The GPS of the frame: in a perfectly synchronous network, you'd expect the payload to start exactly at column 10. However, due to tiny timing variations, jitter, or different clock sources, the payload might drift. Function: the O pointer tells the hardware exactly which byte in the payload area is the start of the VC4. This allows SDH to be flexible and float the payload within the frame. The VC4 payload, Virtual Container 4, this is the cargo area of the frame. Location, rows 1 to 9, columns 10 to 270. Capacity, it provides a space of. Components, path overhead, PO, the very first column of the VC4. It stays with the payload from the beginning to the end of its journey, end-to-end management. Container, C4, the actual user data. This is where your high-speed Ethernet traffic or multiple mapped E1/T1 signals live. Summary table, STM1 components, component rows, columns, responsibility RSOH 1 to 3, 1 to 9, framing and regenerator management. O pointer 4, 1 to 9, locating the start of the VC4 payload. MSOH 5 to 9, 1 to 9, protection, switching and error monitoring. VC4 1 to 9, 10 to 270, the cargo, customer data plus path management.